Okay. Hi, everyone. Welcome to Meet the Big Tech arm at PoliTO. I'm Leonardo Gallina, the head of Logistic and Fundraising Committee at the MUNU chapter of IEEE-HKN here at PoliTO. And today we have the honor of hosting 3 engineers from ARM Cambridge. Each of them will talk for about 30 minutes, and after that we will have some time for Q&A. Thank you for being here, and I leave the floor to the speakers.
Hi, everyone. Can you hear me? Good. It's always good if you can't hear me. Well, then again, isn't that good? So, welcome. It's great to see such a large audience in a really, really nice lecture theatre. I've got to saw your campus today a little bit, and I have to say it's really nice, and the city's really nice as well. So, enjoy your time here. That's all I can say. So, I'm going to talk a bit about M-Profile. So M-Profile is the ARM architecture associated with microcontrollers. I'm sure most of you are familiar or a little bit familiar with microcontrollers, but what I'll do is give you a little bit of a history of both the architecture and ARM IP in the microcontroller space. But before that, a little bit about me. My name's Alan Skillman. I've been working for ARM for quite a long time, but I didn't start that way. My background is actually in physics. So my early career was all around high-energy particle physics. I spent a lot of time in CERN, which is an exceptionally cool place if you ever get a chance to go there. Lots of computation being used in interesting ways right on the forefront of technology. I joined ARM in 1998, and I've been in quite a lot of different areas. So I started off as a software engineer, and then I moved on to hardware. I spent a lot of my time in ARM working on CPU design and leading quite a few projects then. And then after that, I've recently moved on to a completely different area called Central Engineering, Central Technology area, which is very heavily involved in system-level investigations. But I'm going to be back out a little bit now, and I'm going to talk about more of the CPU area. So, summary of what I'm going to talk about. Effectively, we're going to do a little bit of an introduction to the ARM microcontroller architecture and use cases, and then we're going to spin through a few examples of the products we've built over the years with some interesting facts and figures along the way. Hopefully it's going to be interesting and not too boring. So let's start off. So here's a good question. What is a microcontroller? And of course, what everybody does, and this is now shows the age of me rather than this talk, is of course you guys would go to ChatGPT and say, what's a microcontroller? But no, I haven't got it installed, so I go to Wikipedia instead. And surprisingly, Wikipedia's entry is pretty good. This is a little bit out of date. There's some comments to technologies that are fairly old now, but it's a pretty good description. Essentially, a microcontroller is a small computer. It's primarily designed to work in embedded systems. It won't be showing up as some huge... that was not my car, by the way. Don't expect to get one of those. No idea where that came from. Maybe it was an example of an embedded system with a microcontroller. There would be plenty in there, yeah. And in reality, it's kind of like a system on chip. System on chip, SoC, is a very popular term. Pretty much all of the microprocessors, microcontrollers now are deeply embedded in system on chip. So essentially, a group of different technologies joined together with either a single purpose or a There's a lot of cars coming up. Yeah. Anyway, so let's have some examples of microcontrollers. So these are the ones you probably would normally think about. So the microcontroller sits deeply within the tech you use in the household, be it the sort of cool stuff you sit in the evening watching, Netflix or whatever, the latest streaming service, in your TV, while your washing is gently going on in the background, or students, maybe your parents are washing it in the background, I don't know. The microwave that you cook your dinner in. Surprisingly on there's a coffee machine. Apparently that coffee machine actually contains a 32-bit microcontroller. I don't know why you need 32 bits of microcontroller to make your coffee, but apparently it must make good coffee. It's not as good as the coffee I've had today, by the way. So, and of course, cars. Cars these days now contain an increasing number of microcontrollers. They're in the braking systems, they're in the chassis systems, they're in the infotainment systems, they're everywhere. And of course, on the left there, an industrial robot. So everything's built by robots quite often, and now, of course, you need microcontrollers within robots. So those are the normal kind of microcontrollers you would see, but they're now involved in a lot more devices associated with the Internet of Things. You can guarantee everything on here has got the word smart in front of it, because apparently everything's smart now, apart from me. So you've got smart speakers, you've got a smartwatch there, you've got a smart thermostat, so you can set what temperature your flat is when you get back home in the evening. You've got a smart doorbell. I've never understood these doorbells. You press them, and they make a great big noise outside. Why? Because the person's inside. Oh, I don't understand that. And earbuds, of course. So all of these devices are connected to the internet. They're what's quite often called endpoint. And in that endpoint, they quite often these days are doing artificial intelligence calculations. So a lot of devices will, rather than sending your requests to a server to do that work, they're now being done on the actual device, which means the microcontroller involved has to be a lot more computationally aware. Further, these two devices might not be the ones you think of when you talk about or think about microcontrollers. So your mobile phone contains an application processor. Could be a Snapdragon, it could be an Intel-based one. Very rare, but could be. And you don't usually think about microcontrollers, but actually there are a lot of microcontrollers in these devices. They're not the ones running the operating system, but they're the ones dealing with the audio, they're dealing with the touchscreen, they're dealing with the power control. You'd be surprised how many are actually in the keyboard of a laptop. So they're absolutely everywhere and absolutely essential for today. Okay, a little bit of ARM MCU history. So here's a question to the audience. Who wants to put their hand up first? Does anyone know what the first ARM microcontroller part was? Your professors are watching. Anyone? Okay. Do anyone from ARM know what the first ARM microcontroller was? Anyway, it's surprisingly early. It's actually 2001. I'll get on to a lot of people might expect it to be one of our Cortex-M series, but actually it was very early. So it was ARM17MI was a very successful piece of ARM processor technology, fairly early version of the architecture, running at fairly low clock speed. What's quite interesting here is you see it's manufactured at 0.35 micron. So that is 350 nanometers, which makes it roughly 100 times bigger than a modern SoC at around 3 nanometers. So just gives you an idea about how technology's changed since 2001, 100 times smaller than a modern SoC. So M-profile architecture. So we have a specific architecture associated with microcontrollers. You might be familiar with the ARM application architecture, our 64-bit architecture, which is used in pretty much all of our application processors. Microcontrollers are a little bit different, and they're different because they have to adhere to essentially 3 golden rules. So high availability, deterministic behavior, and configurability. So to rope those out a bit, so essentially the device has got to be sitting there waiting for events to happen, and it has to process those events. Essentially, to do that, it's got to have low latency access to resources. So it's got to be able to access the I/O, it's got to be able to access the peripherals, even in the memory, and it's got to be guaranteed. So you can't have anything else preempting it. or it must have the highest level of preemption. It's got to be deterministic. So typical application processes, they don't have to be deterministic because events don't have to happen at a specific time. So they could be busy doing something and have to wait for something else to complete and then go on. But in real-time processing, if you're reading sensors and you need to take results of them, be temperature or gyro or something like that, it's got to be deterministic. The third is configurability. So one thing about these microcontrollers is that they have to be low cost, incredibly low cost, because some of the devices that go into them are very low cost. So in terms of the actual cost per unit, they have to be small, which means that when they're implemented, they have to be scalable, and a particular design can be used across multiple applications. So typically, a microcontroller product can be configured in many, many, many different ways, from a minimal configuration to maybe quite a complex, large configuration on the same design. So from an ARM and a hardware design perspective, it's quite a challenge. And when I said 3 golden rules, of course, I was lying, because nobody ever tells the truth these days. Actually, there are 4 golden rules. And the 4th one is energy efficiency. Your energy efficiency is how much work you can do per unit of watt of electricity you burn. And essentially, that's the same as battery life. So if your microcontroller is sitting inside your earbuds, and your earbuds are in your ear, and you're halfway through your run, and it runs out, you get annoyed, very annoyed, because you have to then charge them, and then you can't listen to your latest music, and it's really annoying. So then you have to listen to everything else. So yes, battery life is incredibly important. Now, I joke about the earbuds, but there are lots of applications where that lifetime could be really, really critical. So I'm going to talk a little bit about the architecture features in these ARM microcontrollers, or the ARM M-profile architecture, to give you a flavor. I might skip through these fairly fast, but I'm sure we will be sending out these slides so you can read them afterwards. So, or obviously you can ask questions, don't worry. So the first thing is, over a normal ARM application processors, we have a simplified instruction set and exception model. So it's only a 32-bit architecture. The general application architecture for ARM is 64-bit. Obviously, 32-bit affects the size of the registers affect the size of the processor, the size of the processor affects the price. So low is the better. We only have 2 operating modes. We have an operating mode called thread and an operating mode called handler. So thread is normal, what you might call user mode execution. Handler is handling an exception. Most microcontrollers, when running, will be in handler mode all the time, because when they drop back to thread, there'll be another event for them to handle, and if they're back in thread, they'll probably turn themselves off anyway, because there's no point in burning power. So generally speaking, your applications are waiting for events, the events get triggered, you go into a handler and do the work, and then you stop it. Privilege is a little bit different as well. You can have privilege in thread and handler, but you can't be in unprivileged or user space in a handler, so handlers are always privileged, because they have to access peripherals. The memory system is a little bit different. Most application processors have a virtual memory capability. That is that they can translate virtual addresses into physical addresses. They can map a flat virtual address space into a segmented physical address space. We don't have that in microcontrollers. In general, it isn't needed. And even if you had it, it would lead to additional latency, because obviously to translate from virtual to physical address, you have to fetch a page table. Fetching a page table could stop you from being able to read a peripheral, so we keep it flat. We also have a default set in the address map, so keep things simple. And we also have fully memory mapped peripherals. So pretty much everything inside the processor and outside the processor is completely memory mapped. That means if you write your code in C, I know you guys probably write code in Python these days, but generally on microcontrollers it's written in C. You can directly address peripherals through pointers. It makes it easy peasy to use. In terms of exceptions, so I mentioned that there's lots of events. Events are the key to microcontroller operation. The system sets off events. The processor needs to respond to the events. It needs to execute the appropriate code, read the data, do the calculations, write the results back. And in order to handle those events, we have a dedicated interrupt controller. It's called an NVIC, or a nested vectored interrupt controller. Uses vectored interrupts, so the address of the handler is programmed in a table. The whole thing is microcoded. So essentially, once programmed up, an event goes off, the hardware will do the hardware stacking of registers, enter the exception handler, so you can execute your code, and you can drop back out again. This makes it easy to program. You don't need glue functions to do your register stacking and unstacking. Makes it really straightforward. We also provide the ability to preempt entry to an interrupt handler. So if you start an entry and then a higher priority handler comes along, it'll drop into that one rather than the original one. And also what we call tail chaining. Tail chain is when we come out of an interrupt handler, and instead of unstacking the registers and then immediately stacking them back up again, we can join from one interrupt handler to another. All this together makes it incredibly efficient both to write and use exception handlers, which, as I said, is essentially what a microcontroller is doing all the while. So modern processors also have a lot of hardware debug. If you're involved in any sort of hardware testing or bring up, you've probably used debuggers, connected them directly to a processor. So the debug on Cortex-M processors is specifically designed to be efficient for handling microcontroller work. So there's a lot of sort of stuff on here, but essentially it's all about making it easy when you've got a deeply embedded chip on a board to actually debug what's actually executing on that. So essentially we support hardware breakpoints, which are all about stopping on a particular code address. We support watch points. Watch points are all about looking at addresses and data and being able to operate on them. We have a couple of trace methodologies, one of which is called instrumentation trace. This is, for want of a better word, sure everyone's used it, printf debugging. Essentially, you can put something in your code which says, I'm here, and it will write that out on your debug trace bus. As well as that, we do support full execution trace and data trace using what we call embedded trace methodology, or ETM in ARM. And these things can be connected up to an external trace analyzer to generate full reconstructions of the executed trace on the processor efficiently. Now, what's quite interesting here is that debug is memory mapped on M profile, and it's asynchronous, which means that your processor can be executing code, and you can read and write memory as it's executing it. That means you don't have to stop it, which is really useful, obviously, if it's executing some real-time operation. We also support the ability to connect multiple processors. As I said, a typical microcontroller or SoC system will contain a lot of individual processors. So ARM has a feature called CoreSight, which is all about multi-core or multi-unit debug and trace, and M-Profile supports those as well. Okay, so those are a bit of a whisk through some of the features of our microcontroller architecture. Let's look at some of our products. So this is a kind of a timeline of all the M-Profile products that are currently in the market today. It's one thing to note on here is that the timeline is not linear at the bottom. So unlike your sort of normal compute products, the ones that go into your mobile phone or your laptop, essentially where a new generation is produced every year. Indeed, actually, for a mobile phone, new generation of processors tend to come out about every 9 months now. That's the type of cadence that ARM and companies like ARM have to do to produce the products that end up on the shelf in the shops. Microcontrollers are a little bit different. They have a very long lifetime, and they tend to get produced when it's valuable to bring some new technology into the market. So over on the left there, you can see Cortex-M3. Cortex-M3 was the first ARM dedicated microcontroller in the M-Profile architecture. And that came out in 2005, and that processor is still being used. We're still licensing it. So essentially, it's a very long lifetime. So in terms of design and verification, it's really important to get it right. Because in 2025, you don't really want to find a bug in it. So that's one thing. The other thing is that, as you can see, that there are various different generations of architecture. You'll see at the top, we start with V7M. Interestingly, we dropped to V6M. I will explain that in a minute, and then across to V8M, which is the latest architecture we have today. Now, I won't talk about all these devices. It'd be nice if I could, but it would take far too long. So I'm going to sort of whiz through a couple of interesting ones with some interesting facts. Okay, let's start off with Cortex-M3. So Cortex-M3, as I said, was the first dedicated ARM microcontroller intellectual property or processor, IP product. It's kind of the archetype. It was the first one implemented with the architecture, which is the V7M architecture, and incredibly successful. It's a very straightforward processor. It doesn't have complex memory system. It just uses Amber AHB buses to connect directly into the system. And as I said, primarily designed as a traditional MCU rather than an SoC device, although it's been used in a very large number of applications. In fact, it was so popular, after a couple of years, we actually produced a sort of follow-up on it. It's always, the second album is always the hard one to do. Luckily, we managed to nail this one, called the Cortex-M4. So the Cortex-M4 is essentially the Cortex-M3 with additional support for floating point operations and additional SIMD, which is single instruction multiple data operations, which was released about 4 years later. So again, incredibly successful. In fact, when I was writing this talk, I decided to go, I wonder how successful it actually is. So, of course, in the highly, highly scientific method, what I did is I went to Google, and I typed in Cortex-M3, and I got, that's that, 9 million, just 9.1 million entries, which is pretty good, isn't it, actually? The thing is, though, because I thought afterwards, during the time we made Cortex-M3, as you probably know, we have project names. Most people have project names. Somebody who designs a project thinks about, what am I going to call it? Yeah. So when we did this, we were kind of into cats. We had lots of projects called cats. And at the time, the project was called Sandcat. And I looked up Sandcat. So Sandcat's got 307 million entries. So it's more popular. And you know why it's more popular? It's because these things are darn cute. I mean, look. I mean, like, and that. It's ironic, isn't it, actually, that most of our computing is actually being used to house these cat pictures, you see. Yeah, it carries on. They're lovely, aren't they? Oh, so I go on all day. Oof, there, that one's even better. Oh, that one, look. Oh, that one. Oh, looks yawning. Oh, that was. I don't know how many I've got. It's going to be embarrassing if I keep going, isn't it? Yeah, that's the last one. Right, that's enough. Okay. I could have gone all day. It's like, anyway, right, so moving on. So we did Cortex-M3 and M4. They were very successful, but they are fairly area intensive for some applications. So, and as I said earlier, a lot of it's about cost, and cost is about area. So we decided to see if we could build the smallest one possible. So Cortex-M0 Plus is the smallest ARM microcontroller that we have. It's a slightly different architecture in actually that its instruction set is only 16 bits long rather than 32 bits long. It uses thumb only, which is our 16-bit instruction set. But it has all the other features, Cortex-M3. It has the NVIC. It has the memory system control points. It has hardware debug as well, which is pretty fantastic. What's really fantastic is how small it is. So essentially, if you compare Cortex-M0 with the smallest possible application core that we build, which is the Cortex-A35, you don't have to worry about it, but it is an application core. It can run Linux. It's a bit different, right? So it's 154 times smaller. And that's the smallest configuration you can put an A35 in. In fact, you probably would never build an A35 in that. So that gives you an idea how small it is. In fact, some fun facts, right? So there's only 3,990, under 4,000 lines of Verilog, excluding comments, in the entire design. One file. It's quite cool, you can read it. And there's only 700 bits of flop state in the entirety of the design, and 80% of that is architectural. which means that you can't get much smaller because you're using every bit for the state that the architecture says you have to have. So it's an incredible piece of design. I know the designer. He's incredible. It's not me. Not me. I just stand up talking about it. I'll big him up, you know. Okay, moving on. So we talked about ARM v7M and ARM v6M, interestingly. When we moved to ARM v8M, what we did is we decided to say, okay, we've got this v7 architecture over here, and we've got this v6 architecture over here, and they're kind of slightly different. There was some sort of incongruities about them. So what we did is we brought them together into a single architecture in the 8M series. And then the 8M series actually then allows you to go and build what is essentially the lower cost one called base and the general purpose called main. But at the time, what we actually did, because there was a lot of work going on in research around new features and capabilities, is we added a bunch of extensions. And I say extensions, 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 because this isn't actually all of them. There's a lot more. But this is all we add in. So we add in things like security, vector capabilities, some functionality around optimizing branches, because control code has a lot of branches in, the ability to make custom instructions within the design, updating debug, adding performance, and bringing some of the features from a profile in, such as reliability, serviceability, and availability, which is all about making sure your device stays up. I'm not going to go into this. You know, I don't really have the time. If you've got 3 hours, I could go into it. You're probably going to get bored by that point, especially with my voice. But I did want to sort of, because a little bit of humor in this talk. So the vector extension. So you might have heard of the Neon vector extension that's part of the applications core series. So when marketing got hold of this, they thought, Neon, you see, that's what we used to call it. So we'll call this Helium. So when I say helium, I mean the vector extension for microcontrollers. See, it's humor by the marketing guys, because helium's kind of smaller than neon in the periodic table. My son's a chemist. He thought it was hilarious. You're all computer scientists. What? Okay, so finally I'm going to talk about one of the latest Cortex-M processors. There's a lot between, but this one is one of the last ones I worked on, the Cortex-M55. So this is a V8M processor in 8.1 and includes the vector extension. It's pretty advanced. We spend a lot of time looking at the microarchitecture to get improvements in the design, both the energy efficiency, but also to be able to run it at a higher frequency. These microcontrollers, because they have to have very deterministic behavior, it makes them very hard to use techniques that would be used in regular microprocessors, like out of order. They are generally much simpler, but these put restrictions in terms of the timing, which means that the frequency they can run at in a particular technology is actually very restricted. One thing that's interesting here, as I said, is the introduction of the vector extension. So if you look at what we can do there, this is a graph of performance. So higher is better, and about using keyword spotting algorithms. So this is running an AI process on the microcontroller at the endpoint, so in the field, rather than sending any data on the network, and comparing. So keyword is basically when you say your favorite word to wake up your smart speaker. Or if you suffer what I do, my wife's name is Alexandra, and if you're not careful, Alexa wakes up and says, what? What do we do? When I say her name, which is quite funny. But anyway, your favorite name. So what you can see here is that Cortex-M4 and Cortex-M33, which I didn't talk about, but is another one of our designs, are not too bad. Cortex-M7 is interesting. That's actually a high-performance microcontroller. It's designed for high-performance applications. It's a full superscalar dual-issue device, but it doesn't really perform, relatively speaking, much better than the small guys. But then you look at Cortex-M55 with its vector engine is performing, looking at the numbers, kind of 8 times better, which is really quite impressive. I've written 8 times better. I should be able to read my own slides. It's terrible, isn't it? Okay. Finally, there's going to be more. Marco's going to talk a lot more about this, but I thought I might give a couple of slides on functional safety. So microcontrollers are used in environments that require functional safety. So when you're in an automotive or you're in an industrial setting, it's really important that safety is taken into account. And generally, when we talk about functional safety, we're talking about standards such as ISO 26262, which is the standard associated with automotive or industrial, robotics, for example, the IEC 61508. Those numbers get burnt into your brain if you do this. You can't, 26262 is like comes to your mind. So these standards, what they say is you have to have systematic and diagnostic coverage of potential faults. So what you basically need to know is that what's the possibility, what's the probability of a fault occurring that you detect or don't detect? Because it's fine to detect a fault, because then you can do something about it. But if an alpha particle goes through your device and it starts misbehaving and you can't detect that, that's really bad. It's really, really bad at 70 miles, 800 kilometers an hour on the highway. So what we do is we build our designs in order to fit with these standards, particularly in the design process. So we build things based on requirements. So we define our requirements for the device, the architecture through to the specifications, the design, the verification, and the coverage. So we can basically show how they are designed and how the design links to the final device. But we also contain a bunch of capabilities within the processor for fault finding, be it sort of looking for checksums within the logic, be it calculating parity or error correction codes, particularly in the RAMs. But we can also duplicate logic, because if you duplicate, then if you fail in one, then you can emit an error just because you've got another copy of it. So I've got a couple of examples for Cortex-M55 finally. Essentially, we usually run it in, or we'd expect partners to run it in two different configurations. So the first configuration is what I've called DCLS configuration. This is the classic way of dealing with fault detection. And what you do is you duplicate the mission mode logic. You say, well, I've got one version of most of my logic, and I'll build another version of my logic. And I'll assume that if one fails due to some random occurrence, the other one won't, and then I compare the results. I feed the two inputs into both versions, and I check the results at the back end. So you can see there's a set of comparators on the right-hand side that generate faults. We go a little bit further than that. What we do is we move it temporally. So you'll see there's a bunch of flops on the back end on the output of the first processor for the comparators. And then as the input to the first processor, there's a balanced set of flops. So essentially, if anything, and we have two different sets of clocks there. So essentially, just in case there's any sort of temporal effect between the two, they won't occur at the same time, which means that we should spot it. And you'll also notice on there that we have other features such as ECC, so the RAMs associated with the one set. We also don't duplicate everything. So if you notice, we don't duplicate the RAMs, and we don't duplicate debug, because debug isn't used in mission mode. So it isn't functionally safe requirements. This is great, and this is typically used for what's called ASIL-D, which is the automotive safety integrity level, which is what is defined in these standards. D is the highest. You have to have 99% coverage of faults. Unfortunately, it's very expensive. You have to duplicate everything. And typically, as I've said multiple times in this talk, duplicating everything is expensive, and everything's about cost, even in your car. So we have a different approach when we don't need quite as high fault coverage level, which is handled by what's called ASIL-B, ASIL-beta, and a different configuration here, which I've called the software BIS configuration. So this works in a slightly different way. You'll notice there's only one set of logic rather than two. And instead of having a duplicate, what we have is a set of software, which we call a software test library, or an STL, which is executed when the main code is not operational. So essentially, ever so often, you'll stop doing the main work and you'll run the STL. And you also have a piece of hardware in the system which is capable of generating some stimulus. So, and when you run the code, what you're effectively trying to do is exercise as much of the logic as possible in a way that tries, if there's any errors, it will stimulate failures. And failures can occur for various reasons, either from easily monitorable responses, you can see there, or failures such that the processor kind of stops working, and then you have a watchdog in the system. A watchdog is essentially something waiting for a timeout. The timeout occurs, it says, oh, okay, I failed, so I recognized. So the thing about this is it's really tricky to write these things. Essentially, that software has to be tiny, and it has to execute really fast, because you only have a certain number of cycles while the system's not doing anything before you have to go back. I talked about real time before you have to go back and actually start doing with real work. So the techniques of building those software test libraries is incredibly complicated, uses a lot of resource, and I think one of my colleagues was involved in the M55 software test library, and it took probably tens of person years worth of work in order to build that. The other thing we do here is slightly different, looking for transient faults as well. So instead of duplicating all the logic, we duplicate some of the flops. You see on the right-hand side there, essentially what we're doing is we're taking the input of a flop, we're taking the parity of it, and then we're checking the parity of the output relative to the output of the flop. And obviously, if something's gone wrong in the main flop at that point in time, then the parity will change, and we can signal an error there. That's a lot cheaper than actually reproducing all the logic, because the combinatorial logic isn't reproduced as well. And we can choose where we put those flops, those duplicate flops to critical areas. Okay. What's quite interesting is Cortex-M55 was actually the first processor to have both ASIL-D certification and ASIL-B certification for ISO 26262. So, and it took a significant amount of time. To give you an indication, we completed the regular release in 2019 of Cortex-M55, and we completed the safety work for ASIL-B in 2024. So it took 5 years to go from the original release to one that has certification. And it's a very complex process, and it's very expensive. Okay, that's it. And thank you very much for listening. I hope it was interesting. No, I can do questions. Questions? Yes. Oh, do we need a mic for the... You might want to shout. I was about to say, you might need a mic for the question.
So is it true that ARM is a fabless company, right? So you don't actually produce your own microcontrollers and processors, right? So you do. So it's not a fabless company.
Sorry. We are a fabless company. But we use our so everything we produce is not silicon. The silicon is produced by our partners. We call our companies that work with us to produce products. Some of them themselves are fabless semis, some of them are sort of like OEMs. So we don't produce any actual physical hardware apart from some development boards. We do that type of thing. But we do use our own microcontrollers in our own designs. So for example, some of our graphics controllers, some of our machine learning accelerators actually contain multiple Cortex-M processors within them as controllers. It's actually cheaper to put a standard MCU that's fully verified inside as a controller rather than building a lot of control logic that you then have to go and verify. But no, we don't actually build any silicon ourselves. We ship our IP out to our partners who then build silicon.
No, actually, I asked that question because I was wondering how the validation and verification process worked for you. How did you, like the whole flow from production to verification? And I was wondering, if you don't produce your own microcontrollers, then who do you go to produce them to then verify them for any faults and stuff?
We verify our IP in the context of the boundary of the design itself. So we take our designs, we verify them in simulation at various levels of abstraction, be it unit level or at top level, the complete design. And we do that in simulation. We will do it in emulation, so hardware emulation. We will do it in FPGA. We may have some test chips developed by one of our partners, and we will test it there as well. But our methodologies are fully covering the entire functionality of the design. From a logic perspective, we also do implementation and check at that level as well. But we don't make silicon to check necessarily. Normally, because of the process of working with our partners, by the time we come to full sign-off of the design, there is some silicon we can test. But that tends to be, it may be final product, it may be test silicon. I've certainly had cases working at ARM where partners are very, very aggressive, and they want to actually bring out a product based on early releases of the design because they want to go to market fast. So sometimes, if you like, the final test vehicle might actually be the product level SoC. But over the years, our methodologies, be it simulation, be it formal, be it emulation, FPGA, have become very advanced to allow us to have very high confidence that our designs are correct. It's okay?
I will bring it to you.
So I was wondering, you mentioned you had microcode. Do you also have the ability to later then patch that microcode? Because you've seen like there's been CPU bugs and such in architecture, and having that flexibility, I guess, would be quite useful.
Not in M profile. That's cool. So we don't have this capability in M profile. We do have it in some of our more application level processors. The reason we don't have it in M profile is adding a programmable layer to doing this is redundant logic, which again I come back to cost. But the technique is very well known, and you're absolutely right. It can be a lifesaver in certain types of applications.
Hello. I wanted to ask, what is ARM's commitment or contribution towards open source community? Are there any parts of the code that, not necessarily code, but like designs or anything of that sort that is open source and that ARM relies heavily or contributes heavily towards? And maybe you can talk something about that.
Not in the open source hardware community. So ARM architecture is proprietary, and all our designs are proprietary. We do license our architecture out to partners that may want to build their own. There are lots of examples out there I'm sure you're aware of. We do contribute and work very strongly with the open source software community. So something that makes ARM ecosystem very, very strong is the fact that it's very wide and very heavily used across the world. It's really our sort of secret weapon because ARM technology is available in pretty much every tool chain, every software usage, every operating system, then it makes it a very wide community. So we have a very strong engagement with the open source software community, but the ARM architecture itself is proprietary. So for example, if you were thinking about RISC-V, for example, we have a very, very different model to that.
And you mentioned software, and I'm wondering, seeing what happened with the latest laptops that came out with Snapdragon, I think that one of the major issues was the lack of development of Windows on ARM. And how long do you think you are from a really strong software for the consumer market? Because I think that nowadays it's really hard to see some, apart from the MacBooks, it's really hard to see someone buying an ARM laptop because it's so, I mean, like Windows, it's so strongly built on x86 that it's, I mean, it will probably be very tricky to shift to an ARM-based software.
I completely agree. I have to say myself that I've spent years hanging around Best Buys or the equivalent shops looking for that ARM-based laptop. Unfortunately, it's been a very slow kind of bring up of this market. If you take out Apple, because they've kind of gone vertical, one of the problems is that PCs have to be very general, and they have a huge legacy of software, whereas Apple has the ability to basically be completely vertical. They can just rebuild all their software. They've switched architectures multiple times, and it's fairly straightforward to them. It's much harder for Windows. Windows was x86 initially. There's a lot of legacy. There's a lot of legacy that still runs on your PC, that's 32-bit, which is kind of hard to get going. And of course, ARM came into that game later. But it is moving. We work with our partners around deployment of Windows capabilities within our architecture, within our implementations. And obviously, our partners work with both the operating system and the application community to bring that in. So I think the tide is turning, but it's slow. And obviously, there's so much legacy in the market, and it's all about the applications. In reality, one of the earliest people in ARM made a comment once at a conference I was in, which was that it's all about the software, stupid. So we do hardware. We spend a lot of time designing hardware and thinking about hardware, but in reality, it's the software that runs on it, which is the most important thing. And so if the software isn't ready, it's very hard for the hardware to take over. In fact, if you're an OEM producing a laptop and you produce a nice ARM laptop and it goes out there and you think it's brilliant, and then the first review comes in and says, I ran application X, which I like, and it didn't work properly, then suddenly your laptop isn't very popular anymore. So this is kind of where it's coming from. But I think it is coming. You should see it. I should see it. I want to go in Best Buy and see all these ARM laptops. We've got time for one more?
The last one.
This might be kind of loaded, but do you think RISC-V and the open sourceness of that architecture might take some of your market share away, or on this regard?
As a very loyal ARM person, no, I'm still going to say, yeah, of course. I mean, I think they have a different way of working. They potentially have even more people that can work on it. So it's bound to take some. I think it's, what I would say personally, and this is my personal opinion, I won't speak for ARM here, you're going to record me, and I'm going to get it quoted back, is that RISC-V in the IP space, so companies that build IP and then sell it out in the same way ARM does it, I think is an incredibly hard market. You've probably seen multiple RISC-V companies that have sort of come up and then kind of gone away. However, our silicon partners are very, they are completely able to say, well, let's build a RISC-V core to use as this small controller within the device. So clearly that it has an effect on companies, the IP companies like ARM. And I think it's always good to have competition. I think when, I've been working for ARM for a long time, and during that time, there was a lot of competition. A lot of companies with their own architectures have come up. And when I'm asked about them, I usually say, yeah, there's nothing wrong with it. It's a perfectly good architecture. You can't say that ARM is better than that. In the same way that ARM couldn't say they were better than Intel or worse. But competition is good because it makes everybody try and do a better thing. So I certainly wouldn't want to be in a space where there is just one architecture, because I think it would just get stale. Okay. Right. There you go.
Thanks, Alan. So this talk is about the ARM architecture. It's a deep dive into one of the features of the ARM architecture that I lead, which is called MPAM. MPAM stands for Memory Partitioning and Monitoring. It's kind of a preview of a keynote that I'll be doing in September at a scientific conference. I have removed a bunch of slides so to fit in within 30 minutes, but feel free to ask questions if anything is unclear. So one slide about myself. I got my PhD from University of Pisa, and then I joined NVIDIA. And I worked there on the Tegra chips, which are ARM-based. In 2015, I joined ARM in Cambridge. And essentially, I always worked between research and designing the ARM architecture. And then what I do now, I lead the ARM MPAM architecture team, which is responsible for designing this specific feature of the ARM architecture. So stepping back a bit, how ARM works, I think Alan has mentioned central engineering. So there's a clear distinction within functions inside ARM. I'm part of the architecture and technology group. And then there's central engineering, central technology, where Alan works. And then we have lines of business that target specific markets. So they care about the requirements of automotive or cloud computing, AI, mobile phones, and so on. And then we have other functions such as finance, legal, and so on. So the ARM architecture is not how things do work, but is essentially, it's a contract, right? So it's a specification. The ARM architecture book is the largest man-made book in the world, which is over 10,000 pages, and is not written by a machine or anything. So it's written by engineers. It does specify the contract between hardware and software. So it's sort of a promise or a standard. It tells software, this is how the hardware will behave throughout the generations of ARM chips. If we write something into the architectures, we usually say it's forever, right? So we need to be really careful about what we do there. It defines how hardware interfaces between itself and different layers of software. So operative systems, hypervisors, firmwares, it's all covered by the ARM architecture. So why do we have an architecture? Because then software becomes portable. So if you write Windows for ARM, for instance, we were talking about that, once done, it will then run on all ARM chips across all the generations. So the other side of the medal is the microarchitecture. So what we've seen before in the previous talk is how things worked. So M55, and then it had all those features in there. So that's more of a microarchitecture. So how the hardware implements something, that's microarchitecture. So within the domain of architecture, there's broadly two types of architecture. There's the CPU architecture, 10,000 pages, is a mix of mandatory and optional features, which means, you know, if you want to build a CPU based on the ARM architecture, you have to have the mandatory features. Depending on your objective, you might put in a number of optional features. You have to be compliant with the ARM architecture if you want to claim your CPU is an ARM CPU. So if an Apple device comes out and it's an ARM-based CPU, they have to go through an ARM compliance process in order to be certified by ARM that they are an ARM architecture. The license to build ARM CPUs is called architectural license, and some of our partners have it. They were mentioning earlier. And it's usually a paid license. That's different from system architecture. So system architecture specifies how other things in the system work, such as interconnect, SMMUs, interrupt controller, and it's usually free to use. So it can be, the specification can be downloaded and has a free to implement clause in there. And it's basically designed to enable software standardization and basically act as a pool for ARM CPUs to be implemented in more systems. So going back to the CPU architectures, there's 3 profiles in the ARM architecture, which mirror the 3 different categories of ARM CPUs. The M class has been mentioned many times in the previous talk. We also have the A class, that's the high performance application processor. So if you have a smartphone, that's going to have mainly an A class processor. We'll see later, actually slides on that. Which is basically the CPUs that run Linux, Windows, OS X. Those are A class. R class is real time. R stands for real time. It's a class of CPUs optimized for determinism and low latency. So the most widespread implementation of R-class CPUs is in hard drive controllers. So they're basically all the hard disks have got R-class CPUs in there. And then M-class, I don't need to say anything. Alan has covered that. So, just as a visualization of what they end up in. So A-class ends up in routers, the smart thermostats that were also in the previous presentation, some of them, not all of them. Gaming consoles like Nintendo, for instance. R-class, industrial robots, hard drive controllers, parts of automotive such as ABS controllers or other things, brake actuation, things that have to react in a certain amount of time. Cortex-M is in Fitbits, in headsets, in smart bulbs, all of that. So this talk covers a technology, so we said it's called MPAM, that mainly pertains A-class CPUs. So that was an overview. Now let's focus on A-class, high-performance CPUs. And it's all about heterogeneous systems. So heterogeneous systems are essentially a generalization of multi-core. They can be in anything. So they can be Internet of Things, heterogeneous systems, mobile, smart home, server, doesn't matter. Anything can be heterogeneous multi-core, which basically just means it's got more than one CPU, or it's got a mix of CPUs and other peripherals that actually do work and accelerate the workload that's running on CPUs. And those are usually graphic processing units, like, I don't know, NVIDIA, display cards, or Mali GPUs from ARM or whatever. And then neural network accelerators or other types of accelerators, which I call XPU in this slide, so specialized accelerators. And why did we end up with heterogeneous compute multi-core is for the simple reason that we wanted to achieve, as an industry, what we call platform consolidation. So if we pack multiple devices within the same system on chip, It becomes more efficient to run multiple workloads on the same machine. It's cheaper than having to put more systems into the same package. So imagine your smartphone is a multi-core heterogeneous system. It's downloading your emails while displaying your YouTube videos or whatever. And it's doing all of that at the same time, parallelizing workloads over a number of cores and a number of devices. So an example of how heterogeneous are your smartphones again. So you have a collection of Cortex-A processors that's running the operative systems, the apps. You typically have one or more Cortex-R controllers that manage the communication side of your smartphone. So that's called the modem. So the modem handles transactions with the cellular network or Wi-Fi or Bluetooth and so on. You have a collection of Cortex-M, again, previous talk, processors that handle the power management, display, or any other peripheral. And then you can have one or more accelerators, such as ARM-Mali for graphics, video compression hardware, display controller, camera accelerators. There's so many things in a smartphone. And the same goes for cars, obviously at a much larger scale. So you have a lot of controllers that, this is supposed to be a pretty advanced car which has vision capability. So imagine, I don't know, a Tesla or any other sort of self-driving car. So it will have Cortex-A's, running AI workloads for obstacle detection, rerouting, and so on. And again, another example from enterprise and infrastructure where you have essentially a server. This is a pretty old server, but still relevant. That has a collection of peripherals that allows you to run multiple virtual machines on the same server hardware with an hypervisor and sharing accelerators and networking interfaces. So the whole point of all this is that there's a collection of objects in those systems, all of them. It's a common theme that are essentially shared resources, right? So in all the cases that you've seen before, there's a common theme whereby you want to maximize the resource utilization, you want to reduce the hardware duplication, you want to make sure you can pack more things essentially into the same hardware, but what happens? You're creating shared resources. So if you put System A plus System B together into a new System C that's now an heterogeneous integrated system, what you're doing is you're running now workload A, so one, I don't know, email client together with your video game on the same smartphone, but they're now using the same memory. So they're sharing the memory. And what happens when they share the memory? The two things will interfere with each other because software is not it was never written in a cooperative manner. So you don't write your video games thinking, oh, there's going to be another thing running at the same time and on the same machine. So what happens if you play on PC? FPS drops if something else is running because it's not cooperative. So everything that's running on your machine is trying to grab as much as it can from the resources it needs. So that's called resource contention, right? And what happens when resource contention occurs? Again, if you played video games, you know what happens, right? Your experience is degraded and delays increase in terms of responsiveness of the application, network delays, all sorts of things. So resource contention affects the workload performance. In more formal terms, we say that workloads have timing constraints. Those constraints are usually called deadlines, jitter tolerance, activation delay tolerance. So deadline is the amount of time you have to complete the execution of a workload. Jitter tolerance is how much variance between multiple deadlines your workload can tolerate. And activation delay tolerance is I want to start something, how long am I prepared to wait until it starts? And obviously interference can make you miss a deadline, for instance. And to give you a practical example, this was an experiment I did with the University of Modena a while ago on NVIDIA TX2, which is a fairly old hardware that I happen to have worked on when I was on NVIDIA. Basically, it was measured. That's a TX2 in the boot of a car that was self-driving. That was about 10 years ago. So 10 years ago, there was a self-driving car in Modena parking itself. So it was measured that because of interference, the average latency of memory accesses in the TX2 could go up by 40 times, which means that you would get a memory access variability that ranged from 10 nanoseconds, which is the typical latency to read something from memory or write it into memory, up to 1 microsecond, which is crazy, it's huge. It basically means your car would crash instead of park, right? So how do we fix this? We need something that is theoretically called performance architecture. It has to have 3 things. And I say theoretically because there's not just the ARM version of this. In other architectures, they've got equivalent technologies. So this is the theory, and then we'll see how the ARM one works. And the theory says you need to be able to characterize and bound the performance of your resources, right? So you need to be able to have a way to understand how the hardware works. How much is it going to contribute to your delays, your throughputs, and so on. And in order to do that, you have to have monitoring. So performance architecture defines a set of monitors that allows you to measure the utilization of your resources, and compute resources are hopefully known to you, such as caches, memories, interconnects, graphic cards, whatever your applications are utilizing to execute, that's basically a resource, right? The monitors also have to tell you what the current performance is, of the application running on the hardware. And then a good performance architecture has to provide you with a control layer that allows software to decide how the interference is mitigated. So instead of being free for all, and anyone that comes in running on the same hardware gets to take as much resources as it can, a performance architecture will define control hooks, control knobs, as we call them, that allow software to say something like, doesn't matter what happens, I don't want the gaming application in foreground to ever lose frames, so I'm going to raise the priority of that application when it's trying to use the GPU. And all of this is in general called quality of service, right? So it's a way to define an acceptable level of user experience that is then translated into control settings for the hardware and the software. And the way we do this is by misspelling partitioning. I just realized that. So the way we do this is by defining the MPAM architecture, which stands for memory partitioning and monitoring. So the MPAM architecture, therefore, is a way to implement QoS, quality of service, via memory system resource controls. So it defines a standard set of controls and monitors, and it originates from an idea that Google had together with the University of Stanford. It was published ages ago, I think it's 2005, in a very famous paper called Heracles. Have a look at that paper, it's quite interesting. And in that paper, they demonstrated that with a performance architecture, in their paper, they talk about the Intel version of that. With a performance architecture, they could get 30% better utilization of their servers. Now, 30% of Google servers is billions of dollars, right? So imagine, just because you've built your system different, you can run 30% more of Google search or Google email, Gmail, or whatever. So that's a lot of money. Also, MPAM is designed to target, is originally designed to target the use case that we call multi-tenant VM servers, which basically means that you have one server, or let's say a Google server or whatever, that's running multiple virtual machines and multiple applications within the same virtual machines. And what we try to do, we want to try to constrain the virtual machines and applications use of the memory system, so that's caches and DRAM. So how does it do all of that? All of this? It's a feature of the architecture that's built on two principles. You have labels that are attached to memory transactions. So it's an implementation of what's called in scientific literature the labeled architecture. You can look that up as well. There's papers on that. So whenever an application generates memory requests, those memory requests are tagged with what we call partition ID. And there's a possibility of specifying one for instruction fetches and one for data accesses. Software is in control, so Linux or Windows or whatever decides what numbers those will be. And then what happens is that whenever those labels enter the memory system, we hit what we call memory system components. Those are little boxes that we define architecturally around caches or memories or whatever. And those memory system components are capable of reading the labels and managing the transactions in a different way based on the labels. So they can say, if I read label number 2, that's orange or yellow, whatever the color is, then I'm going to give it 40% of the max of the cache, essentially. If I read the number 1, 1 is only going to get 10%. And that's how we implement differential treatment and therefore QoS. And the same goes for main memory. So in main memory, we have controls that allocate a maximum amount of memory bandwidth or a minimum guaranteed amount of memory bandwidth. So to visualize those MSCs, so the MSCs are essentially the orange dots, and they can be anywhere in the system architecture. They can be in level 1 caches, level 2 caches, in the interconnect, in what we call the cluster cache, the system cache, the SMMU, which a unit that translates virtual addresses to physical addresses for devices, memory controllers, so pretty much everywhere. A little bit more detail about the generational labels work. So we have, what we have is support for multiple layers of software, as we saw earlier in the presentation. That's basically a fundamental principle of the architecture. So MPAM implements that by basically defining labeling registers, so system registers in the ARM architecture, where various levels of software can write their own labels. So we have the firmware level that we call monitor level. That's EL3, exception level 3 in the ARM architecture. Then at exception level 2, you get the hypervisor labels that can be KVM or any other hypervisor. At exception level 1, that's your Windows operative system or Linux or whatever. And that's EL1 labels. So that's where the operative system writes the label for its own traffic. And then the operative system is in control of the labels for the applications. So an application is not able to say, I want everything. The control stops at the operative system level. So MPAM 0 EL1, the last register on the right-hand side, that's a register owned by Windows, for instance, that allows Windows to say the Outlook application is never going to get more cache than the video game that's running, for instance, as an example. So this is all dynamic, right? So imagine as you kick an application, you run it, suddenly the operative system can decide, oh, that's going to get a new label, and now I'm going to reconfigure the cache and the memory controller to make it look like there's nothing else running on the machine. So that's how it works. There's many controls defined in the ARM architecture. You have portion controls where you slice something up into homogeneous slices. Can be a portion of a cache or portions of a bandwidth or whatever. There's max-min controls where we limit something, so we try to avoid that exceeds a maximum amount of resource. So never use more than X% of graphic bandwidth, for instance. Or minimum control. So if you're not getting the least minimum guarantee, then I increase your priority so that you'll get it. I don't know if you've already looked at scheduling theory, but there's a very well-known scheduler. A scheduler is an algorithm that basically allocates resources. That's called weighted fair queuing, or WFQ. We have a control that's called proportional stride that basically implements weighted fair queuing. And it's a mix between a fair algorithm that basically gives everyone an equal portion of a share with a bias. So there's a weight component in there. And then we have fixed priority and vendor specific. So MPAM allows third parties to define their own algorithms as well. I'm going to go quick because we haven't got much time left. This is a model of how operating a partitioning control works in an MSC. So what happens is you get an incoming request. So for instance, a memory read into a cache. The cache reads the partition ID. It accesses a settings table where it reads the configuration for the partition ID. And then what happens is there's a regulator, so a piece of hardware, that's microarchitecture, that will dictate how that part ID has to be treated, essentially, right? The regulator and the settings table together affect the control resource. And the end result is the transaction gets more or less of the control resource. I'm going to skip over this example, because I don't think it's fairly relevant. And then we just go through straight through monitoring. So the other side of MPAM is monitoring, because you can never control something that you cannot observe. That's the fundamental principle of performance architecture. So we define a number of monitors in the MPAM architecture. For instance, we can say, we can tell software how much memory bandwidth an application is utilizing in terms of bytes per second. Those monitors can be deployed anywhere in the system. So it can be how much interconnect bandwidth or how much DRAM bandwidth or whatever other bandwidth. We have monitors that tell how much cache the application is utilizing and whether it needs more or less. And they can be filtered. There's more than just one identifier in this presentation. I talked to you about the part ID, but there's another identifier that's called the performance monitoring group. It's just a special version of the part ID. And those monitors have all sorts of other features, such as overflow detection or capture, where you can save a value and then read it later. Monitors essentially work in the same way as controls. So whenever a transaction comes in with its own part ID and PMG, that's the other number, they hit in a table, and the table will tell where to store the data, the value of the monitor, and essentially the monitor stores the value, and then software comes in and reads it. It's quite simple. So as a recap, the MPAM architecture is one piece of those 10,000 pages of architecture. I think now it's about 300, 400 pages. So imagine it's maybe 1% of the whole architecture. It was introduced in what we call the ARM architecture version 8.4, which is a generation of the ARM architecture. And just to give you an example, one of the latest commercially available Cortex, the A78, implements the ARM v8.2. So the 8.4 architecture and future architectures are just now starting to appear in things like Azure Cloud or Google Cloud or other high-performance systems like NVIDIA and so on. So it's an architecture that we defined years ago, and now it's starting to appear. And that's kind of a theme in architecture development. You have to think 5 to 10 years in advance, because it's a kind of a slow process. When you define a new architecture, then you need to write software for it, compilers, and so on, and then eventually it gets built. The specification is available on our website. It's part of the ARM architecture, and currently is, as I said, is implemented by many of our customers, which we call partners, and especially used in the infrastructure market. I think we did cover this, so I don't need to go through it. So this was to give you an example of what we do in the architecture team, and what's the role of someone who works in the architecture team. That's maybe more relevant if you want to work with us. Basically, you have to talk to our partners, customers, right, and try to both guide them and influence them. So you need to say, tell me what you want to achieve, and I'll tell you how to achieve it and how to improve your IP by implementing future generations of the ARM architecture. So in order to do that, you need to understand pretty much all possible use cases of computing. So you need to be not an extreme expert, but an expert of machine learning, cyber physical systems, edge compute, all of the use cases you need to understand. And you need to understand what the market wants. So they want to run Llama, they want to run a video game with ray tracing, they want to run, I don't know, 300 applications at the same time on a laptop. All of that is knowledge that you need to know. And then eventually you need to end up writing architecture, which is a tech skill in itself, because it's written in rules, the rules have to be consistent, and every time you write a verb or a sentence or whatever, that translates into millions of dollars of chips. And if you get one rule wrong, you've screwed up a generation of chips, essentially, potentially. So a career in the ARM architecture team starts as someone who has some background knowledge, so computer architecture, software fundamentals. You need to be really strong at problem solving, creative lateral thinking. It's kind of a, I don't know, skunk works kind of team, so we brainstorm things, we try things out. And then if you get in as a graduate, you're expected to start with modeling tasks, starting from simple system components, designing algorithms, trying to explore new IP functionality. Eventually, you end up becoming an engineer. So you start with modeling larger systems, analyzing the use cases that your customers ask you to think about. It's like, I want to build a self-driving car. Let's analyze that and understand what does it imply. You will eventually start processing their feedback as well. So like Apple comes and says, hey, can you make this thing 10 times faster? And I say, okay, let's work on that. And then eventually you start building technical leadership in one or more fields, which then will become your main domain of expertise. And you end up, towards the end of your career, you can become one of those figures there. So you can either be a project leader, so someone who leads teams and drives cross-group programs, so you run large projects, or you become a world-class expert, like the ARM architect for something, or you become an explorer, like you try to solve an unsolved problem. So you break the ice, okay, let's solve quantum computing or whatever. And then you hand over that project to someone else. And that's the architecture team.
Okay, we will do now a 10 minutes break, and then we'll continue. Thank you.
Hello. Good afternoon. Good afternoon, everyone. I'm Marco Resifo. I'm a sub-functional safety architect and lead in ARM. I graduated here at Politecnico di Torino. I got a PhD, master, and bachelor here. And I'm really, really proud to be here and have this presentation to you. So my topic of today is dependability and how we allow dependability within ARM. So why the dependability? So we want to ensure with dependability that a system can be trusted to deliver its intended service correctly, continuously, and safely, even in the presence of faults or unexpected conditions. And this is needed if we want to build trust in our system, because we want that our system working correctly in everyday usage and with high-stake environment. So, what is the dependability? Dependability is composed by 5 different attributes. The first one is reliability, and where we want that the system work without any failures, reducing the chances of error or crashes. Availability, where we want that the system is ready for use when needed, keeping the system operational. We want safety. We want that the system does not cause any harm and preventing foreseeable loss to people, data, or environment. We want security to build trust and to resist to unauthorized access and attack. And we want maintainability to support the recovery by replacing a device that is faulty. My agenda of today would be this one. So we will see functional safety in ARM. We will see also cybersecurity. We'll see RAS, that stands for reliability, availability, and serviceability, because we can do maintainability, but what we can allow is that the service that is running on our CPU can continue, can perform the intended application. And then I will speak about some challenges that we have in the AI landscape, and a Q&A session, obviously. So, about functional safety. So, functional safety specifically ensure that the system detects and responds to failure in a way that prevents harm to people, to the environment, or to any kind of equipment. And the way we do this is try to anticipate any kind of risk. So we do risk anticipation. We had safeguard that allow us to detect that we are falling in a risk condition, and we build fault-tolerant behavior. The principle, as I said, is risk management. Then we, after we have done the risk management, we ensure that we have safety requirement. Then we comply our product with standards and implementing the safety requirement, and we verify and validate that our safety requirement has been implemented correctly. And what we try to do is what Alan already told you, is try to detect if there are and deal with possible systematic and random failure. Now I want to introduce you to this kind of concept. So a systematic failure is a failure where our system doesn't behave as it has been intended since the beginning. For example, when we build our system, and also you, when you code, sometimes you introduce bug in your application. So dealing with systematic failure means that try to mitigate those kind of possible failure of a system. And random failure are the failure that will arise because our system would have a problem, a physical problem. And the random failure will divide in two kinds of failure. The permanent failure that are the failure that have an infinite duration and they will persist even if we reset the system. Here we have an example of kill, lock, and void that may happen in silicon on the metal line, or transient failure that have a finite duration. For example, when cosmic ray or alpha particle hit our device and they perform some bit flip, some single element upset on the memory or on the flop. And for dealing with those failures, there are methodology. The first one that I want to present briefly is the failure mode effect analysis. And this failure analysis dealt with systematic failure. Let's imagine that we have this system with, this is a CPU, with 4 different stages: fetch, decode, execute, and write back. What we do during a failure mode effect analysis is to understand what are the functionality that every block needs to provide to the system. And we try to understand what are the failure. We try to estimate what would be the failure effect, and we try to have some recommended action to deal with this failure. In this case, for example, in the fetch unit, one of the functions of the fetch unit is to compute the following instruction address. Okay, in this case, a possible failure might be that the address that is computed is not the correct one. Okay, and the failure effect would be that we have a modified instruction execution of our program. And the recommended action that we may insert here is to verify properly the feature. When the guider said, oh, what you do in the verification of your product, we verify extensively that the RTL is behaving as we demand in our requirements. Okay, that is how we mitigate a good chunk of systematic failure. Or we can also insert some kind of heterogeneous redundancy. The second analysis dealing with random hardware failure, and is called failure mode effect and diagnostic analysis. This if it is done in the validation phase. In the design phase is called design failure mode effect analysis. And in this kind of analysis, we try to estimate with some reliability model what is the possible base failure rate of a component implementing a function, and we try to understand if we need to mitigate that failure, adding a safety mechanism, try to gain some diagnostic coverage in order to reduce the residual failure rate. In this case, for example, same system, we have the code phase where the function is the decoding of the instruction. Okay, we may have a failure mode that might be a decoding error that leads still to modified instruction execution because we didn't decode the instruction correctly. It has a base failure rate, in this case, 20 feet. We place a safety mechanism, a CRC, that has a diagnostic coverage of 90%, and so on. If we compute the residual fault rate, is the 10% missing from the diagnostic of the base failure rate, that is 2 feet. The third analysis that we perform inside ARM is the dependent failure analysis. And this kind of analysis try to understand if there are any failure that will affect both the safety function and the safety monitor. So this is the case of the dual core lock set. So we have full redundancy of the logic of the CPU, and we compare it to try to understand if there is a mismatch from the two. In that case, we will identify a failure. But we don't usually double the memory, because it would be really, really, as I say, the PPA that stands for performance, power, and area would drop significantly. Okay? And so we use a common memory. But that common memory feeds both of the copy of the CPU. Okay? So for avoiding that a failure in that memory would result in a dependable failure, we insert a safety mechanism there that is ECC, for example, or some parity. So, and this is basically how we run functional safety inside ARM. We identify and assess the risk of with failure analysis. We do architectural FMEA, architectural DFMEA, and architectural DFA. That are the three analyses that I explained you before. Then we understand where might be the failure problem, and we try to mitigate implementing safety mechanism. We follow the development process aligned with the standards, and then we verify the product. And after that, we will deliver to our partner a safety package where we have development tools like the software test library that is, as Alan explained, a functional test of the CPU in case our solution has this kind of feature. And we also provide our compiler for embedded functional safety application, where we need that the execution of our code is stricted. So it is a compiler that will create a deterministic machine code. Then we have a safety manual that basically is a notebook where we explain how we assess the product that we want to sell within this package. And this say you, oh, we use a CPU with this parameter for the configuration. We use this safety mechanism. The safety mechanism has this coverage. We have those assumptions of use that you have to respect if you want to use our CPU correctly, following the certification that we obtain. Then we also provide the safety analysis, usually only the FMEDA and the DFA. And we also give the development interface agreement where we explain what ARM did for the certification and what the partners need to do for get the certification on its side. Now, if we see the landscape of our CPU, obviously we have different kind of application. We have different way to target that application. Here I'm reporting 4 different examples. Microcontroller example, the Core M55, real-time processor, the R82, application processor, the A720, and a specialized application processor for for server. Obviously, the target level might be different. It depends on the application and on the kind of processor we have there. We may have ASIL-B or ASIL-D for the M55, the R82, and the A720, because we design it in this way. If we want to use this kind of use case in a safety critical component, while, for example, for the Neoverse core, that is the application core that's going to the server, we have only an ASIL-B. We can guarantee ASIL-B only if the partners can still work on it, giving some supervision on the task that is performed by on the application that is running on the A720. So we have about ECC, we have ECC that is optional in the microcontroller, while it's mandatory basically on the R class, and there is a way to optimize the coverage we can get on the memory in the application processor through ECC and parity, and is optional obviously in the CPU that is going into the server. The lockstep support, you already saw that the M55 can go in split mode, so without any redundancy, or in lock mode with the double CPU. The R52 can go in lock mode or in something that we call hybrid mode, where we have the core that doesn't have any duplication of the CPU, but the surrounding of the CPU, all the cache system is lockstepped, and the same for the A720, but the A720 can be also used by itself, so there is also the split functionality, while there is nothing for the core that is going into the server, because that would be too much. For the fault isolation, we have memory protection unit only for the M55, while for the Cortex-R82, we have the MPU and the memory management unit. And with the application core, we also insert virtualization that help you to run different OS and application exploiting hypervisor. Transfer protection we have for everyone except for the application core that is going to the server, because that it would be really impactful for the area cost. And STL, we developed an STL for the M55, the R82, and the A720. No one for the application core that are going into the server. So, cybersecurity. So, how we'll deal with cybersecurity? So, cybersecurity want to ensure differently from safety. So, safety try to see if we have failure inside our system, and we dealt with that. Cybersecurity is, let's build some shield around our system, not allowing any malicious user to use our system, not how it has been intended by the system maker. Okay, and the way we deal with risk in this case is the same of functional safety. So we try to anticipate the risk. We are security guards. We try to build a security behavior, and the principles are the same. So risk management, security requirements, compliance with standard, verification validation, but we need to do two other things. We need to monitor in case someone developed a new attack, and we have to give incident response in this case. Plus, we have to work on the decommissioning of the the system that we release with the security end of life. For doing this kind of cybersecurity analysis, we exploit the STRIDE methodology for understand the kind of threat that will that may appear in our system, spoofing when someone pretended to be something else or someone else, tampering when someone is modifying the data or the code, repudiation where is denying action without traceability, information disclosure, we don't want that there are unauthorized access, denial of service when someone is trying to make our system unavailable to other user or services, and elevation of privilege where someone is trying to get a higher privilege respect to his privilege level that needs to have. And more, we need to understand what are the assets of the system. And for doing that, we need to understand what are the security objectives that are confidentiality. So we want to ensure that there is no disclosure of information. Integrity. We want to have a code that is the one that should run on our system. Availability. We want that the system is working even if there are security attacks there. Authenticity. We need to identify what is the user that is using the system. No repudiation. We need to prevent entities for denying that specific action at event occur. We need accountability and auditability. So we need to trace all the events that user can perform with our system. Isolation, we need to isolate the secure world from the non-secure world. Resilience, we need to maintain the operation capability of our system. And freshness or timeliness, ensure that the data and the operation are recent, and we need to protect to replace attacks. Okay? And what we do is something called threat analysis risk assessment. This is divided in 4 different phases. The first one is the asset identification. For example, in our case, the asset for a CPU might be this, that the CPU need to execute something on itself. Okay, and here the security objective is integrity. So the CPU must execute only the trusted instruction. Availability, the CPU must not be stalled or taken over. And confidentiality, where sensitive data in the register or execution should be protected. Then we identify the threat based on the previous asset identification. So one of the threats that we can identify might be injection of malicious code into the instruction stream. That means basically tampering our code. And this involves integrity and authenticity. And this attack might be performed, for example, with the bug interface or during the bootload, and requires medium capability, because you can do it with, for example, the GTEC. And knowing that, we can start to do risk assessment, where we see the potential impact that in this case is high because and the likelihood that is in this case is medium, because you need only to access to the JTAG for doing this. And in this case, the risk is high, because and the justification is that the code would be, the code execution would be compromised. And at this point, we understand if we want to deal with the risk or not. In this case, is ISO is recommended to deal with the risk, and possible mitigation in this case might be secure boot, code signing, or debug authentication. Now, we have trusted compute architecture within ARM. Trusted compute architecture are foundation of trustful computing system, where we have core principles like isolation, measured boot, attestation, and secure execution. One of the systems that we are developing, and we developed inside ARM, is the runtime security engine that is exploiting a Cortex-M core that allowing an isolated environment for application processor. It allows to boot via immutable ROM and OTP one-time programmable stored the system. The internal OTP is ECC protected, and also the SRAM. We have a secure DMA that is able to load the code from the ROM and the OTP into the RSC. And we had address translation unit for control and memory accesses. We have key management unit that can securely store hardware and software keys. We have a lifecycle management manager that enforces device lifecycle. Basically, we have different stage in the device lifecycle depending what is the moment in which we are using the device. For example, during the test and the validation of your SoC, you want to have the highest grant possible. Then you reduce these grants based on the phase. For example, in development, you still allow to access the debug, and then when you go into the mission mode, you completely detach the debug feature from the system. There is also hardware crypto engine and true random number generator that support cryptographic services. We allow with our system following our concept a secure boot with also attestation and a verification of the images of that we want to boot. And we can detect any tamper attack with our lockstep, and we may also detect side channel or fault injection attack with dedicated countermeasure. Now, about reliability, availability, and serviceability. So, the goal of RAS, because it's called this way, is to protect the data integrity and help to have a system that is highly available for longer period. This is essential and crucial for server application. And here is to explain you what are the RAS features in our portfolio. So there is the Cortex-M class, the Cortex-R class, the Cortex-A, and the Neoverse, the one for the server. And how you can see from the table, obviously the server demands the highest RAS feature possible. That means full ECCM parity on memory. We don't need lockstep. We don't need to detect if there is error inside the logic, okay? Because that it means basically double the cost of the server, things that we don't want. But we want to isolate the fault if a CPU has a problem through PMU, MMU, and virtualization. We want error logging, and we follow the CEP-ER standards, and we perform some log, and we are able to recover a service level, while on Cortex-A, we can recover at OAS level. On Cortex-R, we can guarantee a safe status, and with Cortex-M, the only things you can do is reset. Now, the challenge for AI that there are there for dependability. The first one is about functional safety. So the answer is that, okay, we can trust the result of a model. Can you, do you imagine why we can't trust the result of a model? For example, let's think about an autonomous car. Will you believe everything that comes outside from the AI model? Usually no, because there are some accuracy of the model, right? So in some case, it would not be correct, and we know. So here, we need to understand what is the best efficient way to guarantee that we detect failure inside the system, knowing that we don't want the most efficient system to detect failure when our system has the capability to give an unsafe behavior, right? We need to deal with this kind of problems, and one of the standard, the 8800, is suggesting this thing. So there might be multiple AI models that are running in parallel. There might be a vote machine that try to understand what are the output of this model and select the appropriate behavior. But it's not enough, because maybe this model may fail and give you an unsafe reply. So there is still the requirements to mitigate and overtake the AI decision with something that we trust and we know that would be safer in case our AI models will end in an environment where, for example, they were not trained on, right? Then for cybersecurity, the big challenge that we have inside HAR is allow our partners to model, to protect the model, because there might be, so as far as we understood, there might be tampering attack on the model, leak information on the model, or side channel attack. For deal with this problem, our solution is to perform a secure boot, where we see that the image we are loading inside the system is the correct one, is the model that we want to run. And we perform the attestation of the system, meaning that we bring the system up to a configuration as we desire. We need to encrypt the model unless anyone can take our model. Do you believe OpenAI would be happy to give their model open to everyone? No. So they want the model encrypted. And it's not only that, because when you decrypt, you are using the weight, you're using all your feature, but still you need to protect the execution that might be attacked with side channel attack. So you need to encrypt also the execution. And for doing this, our RSA 100 is one of the possible solutions for that. And for the reliability in the AI landscape, this is not on us, this is another company, but it's worth to mention it because They basically suggest this flow of 4 different steps where you analyze your device, you perform some power, current, and performance analysis during the device. Then you insert sensors inside it that will try to replicate the measurement that you did in the design. You perform some training on the data that you capture from the sensor. Try to understand, okay, this parameter, when everything is functioning correctly, what is their value in our application? And with this knowledge, you may have insight to understand if there are problems inside your silicon. Why ARM is interested in this? Because this thing will go in our system when they will be deployed by our partners, and we need to allow seamless integration with those kind of new feature that will arise the reliability of system. So last thing, so we are a big team that is working on reliability, and I want only to thank these people here. That's all for me. We can have questions.
Oh, okay. Are there any questions? I think no. Okay, we will now proceed with the last part of the event because is connected remotely a graduate from PoliTO.
Yes.
And he will talk about his experience in entering ARM. So the various steps he had to go through.
Sì, vai.
Ok, non si vede però. Ok. Un attimo, prova a parlare. Ok, ti sentiamo.
Yeah. Cool. Okay, I think I have confirmation that I can hear, but I cannot see anyone from the webcam. So, okay, thank you, finally. Okay. Oh, okay. Okay, that's a lot of people. Thank you for showing me this. Okay. So hi everyone. My name is Angelo, and I am a graduate engineer in Harm. I recently joined, but before that, I was actually sitting on those benches just a few years back, and it's quite insane how far I've come now, and now I'm able to speak here, but just remotely. I would have loved to join there physically, but yeah, it would have been it's been quite hard. So it's fine even if we do it with this remotely. So I will just now do a little bit more of a chill presentation, and I will talk a bit how it is for a new engineer in ARM, like what it means to be an engineer in ARM and what it means to be a graduate engineer in ARM. And yeah, I'm just going to pull up the slides so we can just start with it. Okay. Yeah, I think you can see. So what it means for a student from Politecnico to go to ARM, let's say it's quite a special thing, because to go from such an insane path, like with courses and projects and whatever, to go and go actually to a company that, in my opinion, is worth it. It's incredible. So I really want to talk about my experience and how I can just like share it with you and maybe make you a bit more excited for the opportunities we can give in ARM. So let's recap again with the introductions. I am Angelo. My name is Angelo Genuso, and I have recently graduated from Politecnico di Torino in October last year. And my specialization was artificial intelligence and data analytics. I think a lot of you might relate. Maybe some of you won't. Maybe you are going into embedded. Maybe you're doing something else. But let's say I had a lot of courses probably in common with all of you. You probably heard of ARM actually the same way I did, because if a lot of people right there, you have done computer architectures or are following computer architectures, you know that in a way you also have the experience of being able to touch like an ARM board or like something that mounts on an ARM-based chip. And it's incredible to go from something that was just started as a project and now it's just like, oh, it's my company. But other than that, if you know the specific specialization, you know that you also have some specific courses that, in my case specifically, I liked, like the big data one, the machine learning one. I had a lot of fun, but that's why I'm here. After that, or like in the middle of it, I went into Erasmus for 12 months as a student in Enzima in Grenoble. And I had 6 months of courses and 6 months on thesis. And the thesis I had was on about reinforcement learning applied on microservices systems. Microservices systems as in Kubernetes. I want to state this not as a flex, but as a way of saying, if you have a thesis that you think it's worth it, or like if you have a thesis proposal that you think it's worth it, follow it if you think that can help your career. Because a thesis, it's always a project, and I'd like to really tread on the fact that it's always a good thing to search a job that you made a thesis on. Like, let's say, in this case, I made a thesis on reinforcement learning and Kubernetes, and I still wanted to stay in machine learning, and that's something that helped my CV in general. And also, some of you might know me, some of you might not know me. I've been part of the Eta Kappa Nu Minu chapter. This sounds really fun, but a lot of you know me as a living meme in some way or another. But yeah, now I'm a graduate engineer at ARM since this March, and I am based in Lund. Maybe not a lot of you know Lund. It's pretty far-fetched, pretty far away city in south of Sweden. As you can see, close there's Copenhagen, but yeah, other than that, it's a really small city. But it has this enormous campus. You might have hardly heard of the LTH, which is a really good university here in Sweden, and it has a lot of other small companies. Like, we're not small, but they are. There's like a lot of tech companies in Lund in general. And ARM is, we're lucky to have ARM as here, one of them. So let's start with my experience and how I felt the hiring process and what I do in ARM and et cetera, et cetera. So I graduated from Politecnico in October, as I said. I just finished my Erasmus. I was completely scared and confused on how to search for a job. Like, how do you even start? Do you go on LinkedIn? Do you go on websites? Do you go on Indeed? All of these websites really scare someone, and you just feel lost a lot of the times. And also, you don't know what you really want to do. Do you want to go for a PhD? Do I want to go corporate? There's a lot of questions in my mind. Back then, I decided I don't want to go for a PhD. I just want to go and find a job. Not that a PhD is not a job, but I would just wanted to go corporate in this case. And the other question was, should I stay in Italy or should I go out? And for me, I also have some personal reasons to go out, but I decided just to go because I liked adventure and I liked to just have new experiences and most of all, to jumpstart my career in a good company. So I started searching specifically in the Nordics, as I said, for personal reasons. And then I stumbled upon this offer in ARM. But how did I actually get it? So to get this offer before that, before even knowing about that ARM had actually a place here in Sweden, I gathered information about companies that were mainly having an international environment. So a lot of people that would just speak English or would be really able to speak English with you and feel comfortable about it. Like, you don't have to feel guilty for feeling them, to force them to speak English. And that was a really good selling point. And then obviously good salary. Why else are we going out of Italy, right? Then good work-life balance. That's something that some people sometimes, I feel like, in Italy overlook. I read a lot about like work-life balance in Italy, apart from salary being like really bad. So and I also tried it a bit. So I didn't really want to go to Italy back again for that reason. And I also wanted like an offer that could give me a high-level personal and work growth, and in general some graduate programs. And that's what I'm doing. Graduate program is generally defined as like just 1 or 2 years of let's say trainingship, but you're a full employee. Just instead of being just an engineer, you're a graduate engineer. So you go on through a lot of training. You have a really steep learning curve, and then you just rotate into teams. You have the opportunity of looking at every part of the company, doing everything that you can to really get the whole picture and be the best engineer you can be. Because the good engineer in ARM is not an engineer that just works alone. It's an engineer that knows everything about the teams he's working with and the things he's working on, or they're working on, yes. But how did I remember about ARM? It's actually something, it's a little hint that I want to give you. But if a lot of you did the computer architecture course, you know that we programmed on an ARM-based board. In this case, what I did back then was just, and some of you might have done the same. I have done just like a project on an ARM board, like it's making a Tamagotchi, as you can see. So all the logic in C, all the, in this case, all the graphics, that was a mess. But it was a really good project, and it was fun. It was creative, and most of all, it's a good selling point on a CV. If you say, in my case, at least that's the way I saw it, putting these specific project on the ARM, on my CV about ARM board, and then going to ARM, applying and saying, oh, yay, I have an ARM project. It was. It's really funny, but I think that's one selling point for my offer back then. So yeah, anyway, I started applying on ARM's early career portal. I'd like to stress the fact that there is an early career portal that is just containing the graduates, the internships, and the apprenticeships, and that's what I'm going to talk about now. So for the internships, there are sometimes a lot of opportunities for master thesis, summer internships, and part-times. Specifically, maybe I'm talking about this in Sweden. In Sweden, it's really common for either young graduates or non-graduates to go and do an internship in summer. Maybe that's different from our side. And the master's theses usually start at specific periods, but maybe they're more aligned with Italian time. So if you're looking for some master's theses always go to early career if you want to work in this sector, in this specific sector or in this specific company. And also internships are obviously less heavy, and they're testing ground for your skills. That would be that's really the way you also can like just be hired after that. So just do that if you want. And then there's graduate programs. That's what I applied for. My position was a graduate position, and if you get in as a graduate, you get in full time. Like you just start out as a, let's say, as a smaller engineer, which has a lot to learn. And trust me, you have a lot to learn too. And obviously, again, I said again, but those are positions that usually involve a rotation of teams, and you get a lot of input from a lot of teams. You have the possibility of learning a lot, and that's really what the graduate program is about, in my opinion, and also about growing career-wise. And then there are apprenticeships. I don't know much about it. Maybe some people there, since they work in Cambridge, can say a little more about it. But I know they are they are in the UK. I don't know much about them, but that's about it. Yeah. And usually when you try to apply, you see are usually required and qualifying skills, but you can see them everywhere: LinkedIn, Indeed, and also all the job posts websites. But in general, ARM searches for engineers that have good computer engineering and math capabilities, obviously given by courses from uni, and that they are comfortable at programming. You don't have to be you have to be good, obviously, but you have to find yourself comfortable at using a lot of programs. So VS Code, or like using a lot of different languages, learning about different languages, or it might be, I don't know, if you are a hardware specialist, I don't know, other kind of languages, I don't know, but you have to be really comfortable around programming. And then another skill, which is seems kind of obvious, but it's not. It's be open to learn from everyone. Everyone can teach you something, even someone that is an intern. That's what happened some days ago. So like, it's insane. Even with me, or like sometimes even one of my project managers, we just do something, and he was learning from me for how to use like some PyTorch stuff. It was incredible because it makes you feel interconnected also vertically, and it's really good because you're also open to learn from everyone, and everyone there is open to learn from you if you are a valuable person that can give valuable information or valuable knowledge. So let's go on with how actually I got in ARM. I can say this. So the website makes this public, but this is actually my version. So maybe I can give you a little bit more of like a sensation of how actually did you get in, or was it hard? And in fact, for me, job searching was hard. You all know that, and you'll probably know at some point, that job search it's just tiring. It's really tiring, and it's sometimes it feels like never ending. In my case, I had a bit of luck, I have to say, but it was still really stressing. And I want to take this slide just to talk about how, like my hiring process was. So there were 4 steps. The first one was the application, which happened in October when the offer was posted. Now, one hint I can say that is not written here: always periodically check if there are new offers. In this case, in our website, but in general, in every website, always periodically check. Put it as a routine if you're searching for a job, because you never know when an offer might come up. And even if you put you also will put like the newsletter about new job offers, but you also want to have like the jumpstart on other people that might send in applications. So yeah, for the application, I refined my CV. I really focus on my transversal skills. That coming from a Politecnico, you all know that we do a lot of distant courses between each other. Like we did computer architecture once. We did myself. I did big data. So I worked with Hadoop and Spark. And then I worked with machine learning. And then I worked with computer vision. And then I worked with a lot of stuff. This is a lot, even if it doesn't seem like it. You have a lot of skills, horizontal skills, I would call them. And they're really, really important. So also I focus on the projects. The projects is all I had, just like my portfolio. And I had the ARM project, I had my thesis, and I had some projects I did at the university there. And obviously focus on what you feel confident with. I just put like my programming languages, my theoretical computer science skills, blah, blah, blah. And then I also wrote the cover letter. But the cover letter, it's always like, what do I write? There's no really, like, there is a formula for it, but try to be yourself. That's what I always try to say, because I think you can afford in 2035 to be a little bit more yourself in a cover letter. And some hints about this. So use clear and concise language in your CV. Don't be convoluted. Don't just be direct. It really works. Put some emphasis on soft skills. Sounds a little bit sugar-coated, but it is important to be able to work in a team, especially in ARM. And obviously demonstrate passion for technology, where you even as applying if you have no passion for the technology we're making. Then I had my first contact with HR, and I was assigned, I had an assignment to deliver in a week, and based on my position. And then I had a first interview discussing on how I carried out my assignment. But the questions were not more like, why did you do this? Or like, not in a bad way, but like, what was I thinking when I was doing that? And that, I think, is the real deal breaker for a lot of interviews. If you can distinguish in that kind of interview an engineer, like a good thinking person from a non-good thinking person, that's the essential for ARM. And that's what happened. I kind of know what I did, and I didn't use AI. But there, just what happened was I got a lot of questions about what was I thinking when I was implementing that feature. What was my train of thought? What was my, like, what would have been like the client view on this and everything else? And that was, I think, what sold me to the company there. And then I got after that interview, and actually it was pretty funny because I was already going to Sweden for personal reasons. And then they called me and they asked me, hey, Angelo, do you want to come to Sweden for a physical interview? And I was like, oh, but I'm already boarding a plane. But yeah, the final interview happened in the end of November, and I met the teams, and just to assess if I was a good fit for their teams. And about these interviews, what I can say is try always to be yourself, and obviously try to get there a bit prepared. Obviously, you should know about ARM before at least the final interview. You should emphasize your interest in our unique culture. So, like you can see in the website, we have a lot of DEI initiatives. What we can do as ARM, a lot of stuff. Just you can just Google it, and you can find a lot of information before the interviews, and that's really good on our side. And also demonstrate problem-solving skills and creative thinking, because these are technical interviews, and you now know better than me that it can be hard, and you should try at least to do it with some kind of criteria, and I think that's really important. So what do I do in ARM? I cannot go too much into detail because I prepared the slides, and I don't have clearance. But I work as a system analysis engineer, and I'm in the central engineering machine learning team. Probably one of the people before mentioned it. But yeah, even if I'm a central engineer, I work still in Lund, because there are some teams that work together from Cambridge to Lund, but they're just physically separated, but they're still working together. And generally, my objective is to provide the target teams, that's all the teams we're working with, that they're providing us frameworks that they want to be tested. We're providing them with relevant data, assessing their framework functionality and efficiency, meaning we have, let's say, a dashboard giving some valuable information about how a framework is performing, its efficiency, its metrics generally. And just having a way to test for regressions. frameworks to test these kind of regressions when you have such big projects are fundamental. And also some dashboards to visualize results are nice. And a lot of more things that I'm still learning about. And I'm keen to get my hands on. So yeah, repeating myself, I create testing pipelines. I aid in bringing up CI/CD thanks to tools like Jenkins on the right or Docker. Yeah, and the testing pipelines automate image creation, framework testing, test retrieval, and so much more. And the keyword is efficiency there. My offer is for a system analysis engineer position, and I work with machine learning mainly. So my main language is Python, but in the future, I don't know what the future will give me, but likely I will stay on that path. And it's really well specified in the offer that Python was a good, like you gotta have good requirement skills good skills in Python to be able to work properly. And that's something I focus on also on my CV, and that's where the projects went, or at least one of them, which was my thesis. So really finished about what I do at work, just because I'm just here from 2 months still, so almost 3 months, but still I don't have enough experience that I can speak about stuff that I can be really confident about. But what I like about working here, and this is more like I want to give you people an little window of how I feel as a graduate in ARM. And work-wise, I can say that everyone is really helpful. Everyone just tries to make you grow, not just as a worker, but also as a person. And I feel like everyone here is really caring for each other and caring for people that can become good engineers, not leaving anyone back, because you're all trying to do this as a team. Another good thing that I really liked, and I still like it about ARM's culture, is that even as a graduate, you're not taken by hand too much. You're directly thrown into the projects. You learn by smashing your head on the wall a lot of times. But that's really a good way for us, at least, that we have those capabilities as people from Politecnico, to just smash our heads in the wall and try to make things work for a month until actually we understand how they work. And that's great because there's a lot of the steep curve, the learning curve is really steep at the beginning. But then once you get the hang of it, you really learn how things go. And it becomes fun, really fun. Every time I go to work today, these days, and I feel like it's not boring. And that's great because it keeps the work inspiring and always keeps the idea flowing like water. It never gets stale. And maybe it's just my position, but I like that I am not confined into my own office. I always go to speak to other teams. I always go to speak to people in general because you can learn a lot from them. And you can learn a lot about stuff that they don't teach at university. I'm learning a lot, as I said before, about Jenkins, about PyTorch. I didn't know much, Docker, a lot of stuff that in some courses they might be taught, but not in all specializations. In my case, I didn't know that much about Docker or Jenkins. And also every day you learn a lot about how to make better design choices, because here in ARM, usually when we code, we have a lot of checks between us. So we go through Fort code reviews. We do a lot of these stuff, and this stuff makes you better because you're not coding just for yourself. You're coding for a big project, and obviously you need people to check it out, and they can give you feedback. They can give you a lot of information about what you're doing wrong, what you're doing right, what they like, and what this might not be good. So this is a really great learning opportunity. And also you learn a lot on how to work with other people. Again, working as a team is essential in big companies like ARM. So if you already have that kind of soft skill, you already have a good advantage. And about non-work related stuff, I I would have never told, maybe I would have, I don't know. But in ARM, there's a lot of focus on DEI activities, a lot of focus on volunteering, and a lot of focus on communities within ARM. And that's something before, as an outsider, I didn't really expect to be this much of part of like the life of a worker in ARM, an engineer, but it is. So what is DEI? A lot of you might have heard of this acronym. It stands for Diversity, Equity, and Inclusion. It's all of those kind of activities that bring people together, eliminate bias. A lot of this stuff is done in all offices in ARM, and there's a lot of opportunities for these kind of team buildings. There are like a lot of breakfasts, lunches, dinners for those who like food. Me too, honestly. A lot of team activities, usual events, summer, winter events. But apart from that, a lot of events, activities. And like, let's say yesterday, pretty funny. I didn't take the picture in the slides, but we had a potluck. So everyone brought food from their country or like their adopted country, and I brought 3 kilos of pasta, but it was really, really fun. And I think I met some new people there, and it's always a good opportunity to know each other and to just socialize, which is great. And some events are also kind of special because if you are a graduate, you have a special conference you can attend to, which is called the Global Conference for All the Graduates at ARM. I have never went, and I'm gonna go this fall. I think it's gonna be real fun, and I cannot wait. And then there's also focus on volunteering. It makes me feel nice doing some volunteering hours because you in the company you can use part of your time to do volunteering, and you can choose a cause. Let's say you want to go and work for the Red Cross and help like people, or like help homeless people, or like help other stuff. And it really is incentivized in the company. You really are given credit for what you're doing, and also you feel good. Like generally volunteering, it feels like a great part of what I'm doing at ARM too. It doesn't make me feel just like an engineer, but it makes me feel like a person. And also there are several community groups you can join, like women and non-binary Lund. That's specifically for us, women at ARM, early careers, ARM graduates, us, and a lot more. And yeah, that's about it. I have really nothing else to talk about. This was just like my 2 cents, my experience as working in ARM. Sorry, I still am working in ARM. So a little shout out, a little thing I want to say is periodically check the early career portal. As of now, probably there are not a lot of offers, but in the future, who might know? It might be you. You can find something that suits you, and you might be called. So periodically check it, stay up to date, and take every opportunity you can. And also a little hint, since I know you're all studying at Politecnico, likely, yeah. Use the time that you have left at uni to gather skills, gather projects. Projects are important in the CV, and really, you have a lot of opportunities there to speak with a lot of people that, at least in English, okay, but you have a lot of opportunity to speak to people from different cultures, and this is a jumpstart when you go out. If you want to go outside of Italy, it's really a jumpstart because it really makes you open to everything. And finally, a few encouraging words. I know job searching can be hard. I hope you can take your opportunity in ARM. Just know that I recently made it. If you find a good opportunity, you can all make it because we all have the same skill set basically when we go out of Politecnico. Like maybe someone has different courses, maybe someone has different skills, maybe different projects, but all of you can make it. I want to make this really stressed because it's hard when you search for a job to feel valuable and skillful, but please know that you are. know that you have a lot of skills and you can achieve a lot. So please, there is a reason you made it until here. Don't give up. And that's my final words, because yes, this is it. Okay. Thank you, everyone. I cannot hear or listen, so I don't know about questions. Daniele, please let me know if there are any. But yeah. Ooh.
Questions?
And I cannot hear, so wait. Ah, it's here because I was muted all along.
Wait,
That's,
can you hear us?
yes, yes.
Okay. So, are there any questions? Seems not.
Yeah, it's fine.
Okay.
Okay, it's been
Thank
fun.
you.
Ciao Angelo, grazie.
Ciao.
Okay, we finished. Thank you everyone for attending the event. And just a quickly reminder. Okay. No, mi sa di no. Okay. Remember to scan the QR code if you want to apply in ARM, and also we have a QR code for the to a Google form to express your talks about the event and tell us if everything was good. And just a second. Okay, no. Yes, this one. Okay. Thank you and have a nice day.